Hello and welcome to the podcast According to Sci-Faith, where we discuss topics revolving around the compatibility of science and faith. I'm Joshua Göcking and you're listening to According to Sci-Faith. Preview of the episodes 33 to 36, Wheels Within Wheels. Episode 33, The Scientific Method. If you're a regular listener to this podcast, then you maybe have heard me several times talking about the scientific method and its importance. And also I was regularly trying to distinguish ancient science like the ancient Greeks did it from modern science by establishing that this scientific method was basically the difference which made this change, which led to the scientific revolution, which led to these huge changes, which we also will be talking about later. But in this episode, I want to talk about the scientific method in general. What is it? Why do we need it? Why is it so successful? And more than that, I want to look into how the scientific method came about, how we came to this methodology that has been proven to be so successful. So the scientific method is, there are different founders you can call for this that established this theory. It was something that was established organically. Some traces of the scientific method you can already find with the ancient Greeks, but for the most part, it really was established later during the Renaissance period, during Newton, and so on, during modernity, which is also why it is often called modern science, and which is why only then the thing we today call the scientific revolution was unleashed. And one of the people who were most behind this was one of the founder, basically the person who can be considered the founder of the scientific method, if there is such a person, would be Isaac Newton. And let's first look into what the scientific method is. And basically, when we talk about science, the word science basically means knowledge. But what kind of knowledge, you might ask? There are different kinds of knowledge you can have. You can say, I have knowledge like an intuition. You can say, I dreamed something and I think this dream is more than just a dream. It is a revealed reality or something. Then you can also say this is some kind of knowledge that you got in this way. Or in religions there you have revelation knowledge, you call it, knowledge that was obtained by revelation. And in science, usually you do not, or when we talk today about science, we usually do not mean this kind of knowledge. We need knowledge that we gather from nature, and not only knowledge that we, in some sense, gather from nature, but by a specific methodology, and this is the scientific method. And for this, if you consider, for example, how the ancient Greeks did science, they tried to deduce in their mind how they think from first principles, from principles they believe to be true, how the world should be. And with this, they achieved some success. Some theories of them proved to be true, but some turned out to be wrong, like the Ptolemaic worldview, which considered the Earth to be in the center of the solar system, and so on. So some turned out to be false, and this was not found out because the thinking of them was, if I have deduced something perfectly without any error in my mind, then it has to be true apparently. Then I do not need to make an experiment or something like this and check whether it's actually true. It just is true because I did nothing wrong. I deduced it perfectly. However, that might be even true, but if one does not deduce it perfectly, of course, then it will lead to mistakes which will not be catched because you don't make an experiment to check whether your theory or what you deduced is correct. So what in the modern science came about was more focused on this experimental part, to say, okay, what we observe in science, we need to really observe it, we need to really check it, we need to falsify it. And here you have this word falsify, from false on instead of verifying it in the sense of being true. So what we actually not only want is to check whether the predictions, our theories do are actually true. That's not the only part we want to do. We want to also say that our theories have to exclude things, have to say things would be not fulfilled if this theory were true. And if we then can check that this is then we can use this to try to falsify this theory, to try to prove that it is false. And if we cannot manage to do so, then it's a pretty high indicator that the theory is indeed true, because we couldn't claim otherwise. So it's a kind of even more strict way than just to say, okay, if your theory predicts something and we can see it in nature, then it is true, and then we will accept it, because then you could do a lot of cheating and basically create theories that can basically explain every phenomenon. And if there is if it exists in nature, you can say, yeah, my theory is true, wonderful. And if it doesn't exist, yeah, well, then you since you do not falsify it, since you do not have this mechanism, you basically lose nothing, and you can say your theory is true. But you will see that if you think about it, that this is not a really helpful theory, because then anything goes, anything can be explained. And in this way, if you can explain anything, then actually you are explaining nothing. So such theories do not hold any value, and therefore it is important to not only verify theories, but even more than that, to be able to falsify theories. This is really important in science, and that's why we are talking about theories being falsifiable and not only verifiable. So this is one crucial aspect of the scientific method. There are some other aspects that also are important. For example, it needs a theory, or the results of a theory need to be reproducible. So if I measure something to falsify a theory, then this needs to be reproducible. I need to be able to make this experiment several times, and all the time I need to achieve the same result, falsifying or verifying this theory. And also there is also this condition that it needs to be intersubjective. What is meant by that is that should not depend on the person or the state of the person who does the experiment. It should be interchangeable. It doesn't matter who or where he does it. It should be the same everywhere. So this is also one condition, but those are weaker conditions, and also in a sense not always applicable, because there are also branches of science, or what one would consider, at least in some sense, science, where this is not possible. For example, already in physics, if you look into physics, if you look into the Big Bang Theory, there we are dealing with something that has happened. Something that has happened and will not likely happen again, or at least not for us to observe it. And therefore, we cannot say we reproduce it. We cannot have it again to measure it again and again and again, because it only happened once and it is in the distant past, and we weren't there to observe it. So we can only make deductions about how nature works currently and deduce from that how it might have been in the past. But we cannot reproduce any observances from there, at least not in that magnitude. Also, of course, history, the science of history, if you want to consider it as science, there you have the same problem in the theory of evolution. There is basically the same issue there. So there you cannot really reproduce these results, and therefore this condition cannot be completely fulfilled, although you consider such branches of science also to be science. But what you can see from there already is that results that you obtain in these theories are at least not this conclusive, or can, in my opinion, cannot be considered as conclusive as ones where you really have reproducible events, where you really could reproduce the results and really verify it this way. And therefore they are in some sense weaker, the results that you obtain this way. So this is how the scientific method works. So now let's look how it came about. So basically, as I already told you, Isaac Newton is one of the founders of the scientific method. Other who can be considered founders are, for example, Johannes Kepler and other scientists in this time. And the question is, how did he come to this? What was his mindset that he came to this conclusion that this might be a useful thing? Of course, it resulted organically. It was not only him who was working on it, but he was a huge part in it, and he was, I think, a crucial figure in the development of the scientific method. And therefore, it's important to learn why that was, how he came to these conclusions. And Newton's teachers and mentors were mostly were people who were considering things like naturalistic theology, which is basically the idea that God not only reveals himself through scripture, but also in nature. So that was their conviction, and that was a new, or rather new idea that came about in this time. So it was actually not new. It was basically like the Renaissance. Many things were reborn or discovered. But they were of this conviction, and Newton apparently shared this conviction, which you can directly see if you read his Principia Mathematica, where he always refers his scientific results to the God of the universe, and considers his scientific results to be, especially in his General Scholium, he considers them to be clear evidence that this can only have come about with a creator, with a designer. And therefore this was the basis of his work, of his scientific work. And therefore I think you can really argue that this worldview also had something to do with him developing the scientific method. And as I think also was told in the English podcast several times, is that if you look at the scientific method, that the theories need to be falsified. There's also a Christian element in it if you look at it deeper, because it's the understanding that the human nature is in itself fallen and needs to be accounted for, that the mistakes humans make need to be accounted for, and that even if we have a mind that can deduce, as the ancient Greeks thought, that there still might be mistakes occurring that need to be accounted for. Otherwise, it may lead into errors, as some philosophies of the Greeks did. So therefore, this I think is also a sign that the scientific method is based on a Christian worldview, and that Newton, one of the founders of the scientific method, had a deeply Christian worldview is more evidence to that. So this resulted in the scientific revolution, as it's called today, and I think there's no doubt that this has changed the world as nothing or almost nothing else has. And there you can also see this in difference of technology. You can see, if you just look in the time span of technologies between the starting of this scientific revolution, let's say in the 1700s or in the 1600s, and then we look in the technologies we have today, and we compare this to the same time span in antiquity, then we will basically see that there's a huge difference. Just if you look at weapon technology, the weapon technology in ancient times basically remained pretty stable. They were fighting with swords basically all the time. I mean, they had some machines for sieges and so on, but there was not really that huge development in this time compared to the development, for example, in weapon technology that came from the 1600s to today. So there's a huge difference there, and this is due to the scientific revolution. This is due to industrialization, which is of course also a result of the scientific revolution, and this is a result of this development of the scientific method. So there was a huge effect this had on society, on the world, and also on on the West, and therefore it is important to understand this, and also to understand the root for this, as I argue, coming from a Christian worldview. So now later, or if we also look into how we consider science today when we are regarding science, one is often talking about something like a methodological atheism, which is basically the idea that we will not consider God in questions regarding science, that we just will keep God out of it, basically. And the idea is that we say, okay, science deals with the materialistic world, not the spiritual world, and therefore we want to describe the materialistic world, and therefore we will keep everything that is spiritual, whether it exists or not, we will just keep it out of it. So it's not saying we assume that God doesn't exist because we don't believe it, and therefore we behave like atheists. The idea is rather to say that it's just better to work this way because we are dealing with the materialistic and not the spiritual. This might sound really reasonable, but I think in some way it leads into nothingness, basically. So I mean, it sounds reasonable as I explained, that we are dealing with the materialistic, but as we have seen, it is not really scientific. This worldview actually is not really scientific. To do it this way is not scientific, and it was developed much later, only during Darwin's time and so on. This was included in science and considered to be scientifically reasonable, but since the critique or from this side is often that if you just allow something like the idea that a God exists into science, then this will lead to theories of God of the gaps and to just not proper science being properly, science not being efficient, or not being efficient anymore, because everywhere where some gaps occur, one just closes them by saying, yeah, there's a God behind it. But if one argues this, then one first has to explain how it can be that the scientist who was mostly in this way, who was studying scripture more than he was doing science, and who was really coming from this worldview and in his scientific work really portraying this Christian worldview and relating it without making any without distinguishing between those two, how this scientist, Isaac Newton I'm speaking of, how he could be so efficient. I think you could argue that he was more efficient than any scientist has ever been, or at least among those who were the most efficient scientists. How could this be that he was so efficient if he did it wrongly, basically, if he did the thing that is criticized, and bringing his faith or his religious convictions into it, in a sense that he thinks God reveals himself in nature and that he considers this to be the driving factor behind science, without, of course, I mean, you can see this at Newton, that he never did arguments like God of the gaps things. He really described nature in a scientific way, but behind it he always saw a creator who created it always with a purpose. So it doesn't really explain how it could be that many Christian scientists, also later, also after Newton, Johannes Kepler or Michael Faraday, many of the of really successful scientists, also James Clerk Maxwell, who is basically the founder of electromagnetism, how these people could come to these really efficient scientific breakthroughs if their faith would have been in the way of this. So this can just not be. And let's then look it in the other way. Maybe this methodological atheism is a hindrance to science. I mean, it could also be, right? Because if we just assume that there is a God and that the questions that we in science at some point come to questions where we could not exclude God anymore because he does exist, then if we work according to such a methodological atheism, what would then happen? Of course, research would get stuck. We wouldn't be able to continue, because we would just exclude the one thing that would lead us further, that would lead us to the next breakthrough. And I think in some areas of science you can also see this happening, especially in design questions in biology, where the cells appear to really have been beautifully designed, where they act like machines, where you have basic analogies to robots and to computer science being taken in biology, oftentimes, especially in microbiology. So there you see that there apparently seems to be a design behind it, but the scientists there refuse to acknowledge this or try to get away of this or get around this, and then terms like evolutionary design, which basically do not make any sense, come about. So this seems to be the case there. And also questioning regarding the beginning of the universe, of course, there also necessarily it is a question of belief, how you believe the universe came into being, and therefore this should play a role there, which way or ever. So I think there we come to problems because we exclude the thing that might help us for the next breakthrough. And what I'm not arguing is that we need to drop methodological atheism completely, although I think it leads to nothing at some degree, but that's just my opinion. But that's not what I'm arguing for. But I think what we need to do is we need to allow both or several explanations and worldviews to come into our scientific endeavors, because and then let's have like a competition of those ideas, and the ideas that win seem to be the ones who are closer to the truth. For example, there are some cases where apparently intelligent design arguments have made better predictions than predictions from an evolutionary worldview or a worldview of atheism or methodological atheism. For example, Stephen Meyer says about there was this chunk DNA that was observed where it was from an evolutionary perspective. It was thought that this is just some chunk DNA, some chunk that's not useful, some relic of evolution that is not useful for anything. And of course, for somebody who is arguing from intelligent design, this does not make sense. So they argued, no, this cannot be, that has to be mostly useful for something. There has to be some use for it, and so on. And they were arguing this, and in the end it turned out that this chunk DNA really has some use. It really has uses in nature and is being used, and therefore this intelligent design arguing, or that the people arguing from intelligent design were closer to the truth or closer to the scientific facts than those who were arguing from a methodological atheism. So in a sense, this means that there are advantages to such a worldview, and I think even that in the end it would be completely superior to such a methodological worldview. But okay, that's my opinion. But even if you just look at it objectively, it would be reasonable to say, okay, let's have those ideas in competition, and those who work better in this way we will use there, those who work better in that way we will use there, and we will be completely, that would be the scientific ideal in some sense, to say we are completely objective which one we use. Of course this is not possible, but if at least to try it this way, and then to have them compete against each other, and then one will see which will come through, which will be more successful. And I think from the one who's being more successful, one can also see which interpretation of nature is closer to the truth. Episode 34. Is scientific progress on the decline? in times of AI, this might sound like a silly question, but in the last years, this has been discussed very often, especially from scientists who are kind of on the fringes of science, but also from other scientists. And there is this debate whether science is declining or whether we still are making progress. And one of the arguments that is often brought forth, and this is especially in physics, this is brought forth, is that in fundamental research there has been no major breakthrough in the last since the 1980s. And before, it has been the case that roughly every 30 years or so since Newton, there has been a major breakthrough in fundamental science and fundamental research. So the question is whether this is the case, whether this is true. I mean, you can already see that it's hard to nail down how can we really see that there is scientific progress or whether there is decline and so on. And since there are these issues, recently there were studies to really try to quantitatively try to see whether this is true, whether science is in decline or whether the opposite is true, that as we are making more progress than ever before. And there's one paper where they try to find this out, one study where they try to find this out. And what they did is also, first of all, they realized the problem that their publications, the papers that being published, and the amount of scientists have increased in the last years or decades. And from this, you cannot necessarily conclude that there is more progress. No, just because you have more of something does not necessarily mean that you have really also more good things of something. Just you have more because you have more authors does not necessarily mean that you have more good books that are written. So this is just a question between quantity and quality. So, and to measure this, they tried to, or they defined basically a measure of disruptiveness of a paper or a patent. And this is basically showing how much has this paper disrupted the field of research, or the patent disrupted the technology and so on. And they included this measure, and then they tried to basically study how this measure has increased or declined in the last years or in the last decades. And according to the study, this disruptiveness has declined with time. And there was another study who was putting some corrections to it because they missed something there, and they put some corrections on it. And what they found is that with these corrections, there is still a slight decline. However, there is also an increase in highly disruptive papers and patents. So they did not yield such a conclusive result, but they still had to conclude that there is still a decline occurring. So it seems that scientific progress seems to decline. And now, of course, is the question, why is this the case? What is the explanation for this? Are we doing something wrong? Is this just natural? And so there are three explanations, or maybe more, but three main explanations that were brought forth for this. The one is it's just no problem. It's just transitionary. It's just some time, and then it will start to pick up again. Just like, for example, in particle physics, there has been a time where they at particle colliders, they were always finding new particles, and then there was a period or an energy scale where they basically found no new particles, which they later called the energy spectrum, then they called the desert. And but after they passed this energy spectrum, when they went to higher energies, they again found new particles, and so this was just a region, an energy spectrum, a limited energy spectrum in which this was the case. However, there it didn't mean that there are no more particles occurring, and here if one considers this interpretation, it means that this does not mean that science is completely in decline, but it is just a transitionary period. Another explanation is to say that everything has been researched, everything has been found out. We are about to close the bucket of science, and we are about to have found out everything that is to be found out about nature, and therefore the science seems to be declining because we are just finishing up, and then it's over basically. And then there's also this explanation that that science has become basically a factory of publications, where scientific progress is not the goal anymore, but it's just all about publishing papers, about publishing in this magazine and so on, and getting getting cited by other authors, and therefore increasing your value as a scientist. Since in many areas of science, when scientists are being hired, it's one of the measures universities seem to use to decide whether they should hire this person or not is how many papers they have published, and also how often these papers have been cited. So this has been kind of like a market of citations and so on going on, and many scientists criticize that this does not lead to real progress, but just to some kind of paper publishing factory where papers are published just because of papers being needed to be published, just to say that you were working on something, and not necessarily because you did any good work or because you achieved any results. So now I want to mention my opinion to these explanations. I don't think that they all completely fit the nail. I think the first explanation, that there is that is basically no problem, that we are just in a transitionary period. I think this is kind of to be answered with yes and no. There's some truth to it. It could clearly be that this is just some transitionary period, but I think that's not a complete reason. That's not the only reason, and I think there has to be other things behind it why this decline is observed. Then the second explanation, I think, is complete nonsense, that we have that everything is found out, that we are basically at the end of science, that we have found out everything. Many people have said this many times, and they were always wrong. So, for example, Max Planck, who was the founder of quantum theory, he was told to drop studying physics because there's no sense in it, because in several years all the problems of physics will be resolved. And how wrong were they? He created a whole new area of research, a whole new area of physics. So I think this is always wrong, because there is infinitely much knowledge, in my opinion. And therefore, we will, no matter how much we know, we will never know everything. So I think my physics teacher brought this point most clearly. He said, yeah, we know a lot of things right now, but what is a lot of knowledge compared to infinitely knowledge? So this is just the difference that we have there. So I think this will never be the case, and therefore this explanation is complete nonsense. The third point, I think I would also have to answer with yes and no, so that I observed this also. I was not affected by it because I only did a master's degree. I was not doing a PhD or postdoc or something like this. But in this, I met people who were doing this, and I saw their struggle with it, and saw this also happening, that there basically is this pressure to publish, this pressure to have this new publication, and that there is maybe some effect in hindering scientific progress there. But I think this is not a complete explanation, because you have to also consider that this has not, that this is not new. Maybe in this extreme it is new, but it is not completely new. I mean, in Einstein's times, in Planck's times, there has to have been also similar processes going on. This is just how the world is. I mean, there was never a time where basically people, maybe there was, but I think not for a long time, where people were paying scientists just a bunch of money whether they've got results or not, and then they could basically freely do their science and find things out, because they were only focused on progress or not on having their patrons who were paying for their research having to be accountable to them and present something to them to account for their work and for the investment that was made into them. I don't think there ever was such a time where this was completely true, and hence I do not believe that this is really the major problem that is responsible for this decline in science. And I think the reason, or one major reason, I think, is, as I described also in the last episode, that I think science is the most productive if it is based on this naturalistic theology, as it was with Newton, because I believe that science, we had it several times on this podcast, that the creation is a reflection of the creator, and therefore if you get to know the creator, you also get to know creation, and you also get to see where the creator reveals himself in nature. And if you turn this around and try to describe nature, try to describe how nature works, then it is a really big help if you know how the one who designed nature, the one who reflects himself in nature, how he is, who he is. If you know him, then this works a lot better. And I also think historically, if you look at Newton and many of the first scientists who were devout Christians, I think there you see that historically this has also been true. And I think if we return to that and build science on a foundation of faith, where we not say, okay, we explain everything we do not understand away with God is doing it. No, but where we describe nature according to faith, and also use faith as an inspiration for our scientific endeavors, then I think we will get a lot more productive and will achieve a lot more progress. And I think the case that this has been declining, this methodology that was originally used in science has been declining over the years and decades and even centuries. I think this is one reason why we observe, in my opinion, even the major reason of why we observe this decline in scientific progress. And also what this gives you, what faith gives you, it gives you a purpose and a vision, what nature is for, what nature is created for. And I think this leaves no room for nonsensical theories to be pursued, because you can immediately see that they do not make any sense, although you might not see it from the scientific facts and so on. And this makes you, of course, a lot more productive, because you can focus on theories who hold real merit. So I think there is really the breakthrough in science, or can be a new breakthrough in science, if we go back to this foundation of faith where the scientific method was built on. Okay, time for a short break. And as I do it usually in these breaks, I want to give you some insight into my latest novel, Alien Thoughts. So let's listen in. Outside, a fresh breeze blew in her face. After all the time spent in perfectly air-conditioned offices, this air was welcome to her, and she decided to walk the way to her apartment. She left the campus, walked past the bridge, and enjoyed the view of the Heidelberg Castle for a moment. It was particularly accentuated by the rays of the setting sun. Above the castle, on the Königstuhl, the radio towers could clearly be seen. These were already there before the new order was established. Since then, they served for the thought control of large parts of the Rhine-Neckar region. Spellbound by today's particularly beautiful view of the castle, Patricia overlooked a pedestrian who was coming towards her and bumped into him. She was startled when she saw his furious face and was frightened for a moment. Immediately his expression changed, and with a friendly smile he apologized and asked if everything was all right. She answered in the affirmative and continued walking across the Neckarwiese, the meadow at the riverbank. For this man, the situation must have been such that after she bumped into him, he got angry and wanted to yell at her. He came to reason and decided to remain friendly. In fact, however, this was mind control by the AIs in action. In a fraction of a second, the AIs had recognized the emerging thought of anger, and by deliberately playing in deceptively real alien thoughts, they convinced the man to remain friendly. Only when one knew about these mechanisms, as Patricia did, it became noticeable in everyday interactions with people. So in this short excerpt, there is this mind control, which this book is about, shortly described. So if you found this interesting and want to learn more about how this works, how this whole world works, what's happening there, what's the story behind it is, and what will happen in the end, then I encourage you to get the book. You can order it on Amazon as an ebook, and I really would enjoy it if you would read it and also give me some feedback on it and write a review. This just helps other readers to get to know the book and get to see if this would also be something for them to read. Episode 35. What comes after the particles? So if you know about fractal structures, then you might have seen something like the Mandelbrotmenge or the set, Mandelbrot set, it's in English. If you don't have, then I encourage you to just Google it and look at it, and you will see that those are structures where the more you zoom in, they will continue to repeat. So repetitive structures, the more you zoom in, they will repeat, and this goes in this mathematical structures, this goes up to infinity. However, such structures can also be observed in nature. One example would be the fern, basically this plant that you can see usually in forests, where you have these leaves, and if you zoom into these leaves, then you will see this leaf structure be repeated on and on and on until at some point it breaks down and it goes over into a cellular structure. So it is not like in a mathematical way that it is repeated ad infinitum, but to some degree it is in there you can see it is similar to this. It is a fractal structure. However, it does not go on forever this way, but at some point just you will see cells and different structures. But not only in the living nature, in the biological nature, this happens, but also in physics we have this. So you might have asked yourself sometimes that, we know from maybe high school physics that we have atoms, and in those atoms consist of nuclei, and those nuclei again consist of protons and neutrons, and maybe you have even learned, those protons then consist of so-called quarks. But maybe you ask yourself, but what happens after the quarks? What comes next? What's the next level? What's the next lower thing? Does it continue this way on and on and on? And the fact is, or as far as we know, if you look deeper into quarks, what then happens is that you will see further quarks. So similarly to these fractal structures, the closer you look into the quarks, the more quarks you will see. So you will see quarks, and then you zoom in and you see more quarks, and so on and so on and so on. So it's the structure keeps repeating itself. And the question is whether this will continue to go on forever, like with these mathematical structures where it really does continue to go on like this forever, or whether it is like other cases in nature like the fern, where at some degree it breaks down and some other structure occurs. So this is the question, and just to give the answer away right here, the answer is we don't know. We don't know yet. There are different theories, but we just don't know. So as I told with the Thurn, this cell structure at some point will appear, and therefore this repeating structure will disappear. And in particle physics, it's not the case that it is exactly the same all the time. So if we look deeper into the quarks, if we zoom in further and further and further, it is not the case that it is completely the same all the time. It might look the same, but it does not necessarily behave the same. What is meant by this is that some natural constants are changing there. For example, the charges will be changing there. And mathematically, this can be described, or the reason mathematically seen, the reason is that this occurs, so basically in mathematics, or in the mathematical formulation of particle physics, this occurs basically because there are in particle physics theories, which is quantum field theory, there are infinities occurring. So if you try to compute some amplitudes, you don't need to understand what those are, but if you try to compute some results there, then you will have infinities occurring, and this just does not make any sense. This cannot be. Infinities in nature do not occur, so either the theory is completely wrong or you're doing something wrong. And it turns out the theory might not be complete, or this might be an issue, but you can save it if you do some mathematical trick, and this is to absorb these infinities into the natural constants that you have there. Of course, by doing this, you lose something, because now you cannot predict these natural constants from the theory anymore, because you use them to absorb some infinities. However, other than that, is really useful and is a really powerful tool for describing the physics at the quantum level. If you now want to understand what this all means physically, then you have to look at this in this way. So we said we look deeper into the quarks, and then we see more quarks and so on, and we go closer, and we will always see quarks. So those are all quarks. They all carry, let's take it, a charge. Let's take the electrical charge just as an example. They all take a charge. So what this is basically, what you basically, if you are on an upper layer, basically would see is the charge, some charges of all these, the aggregated charges of all these quarks, from which you most do not see, but only see if you go closer. And so in some sense, the actual charge of the quark at the ground level, if there is one, this does not continue to go on into infinity, but if there is one at the core level, then this is basically covered by all these other charges. And this, therefore, the natural constants change. Therefore, the charge is different the more you zoom in, because then if you zoom in more, then quarks who were before covering this charge are now, you are beyond them, you passed beyond them, and now the charge changed because of that, because this charge is not affecting you anymore, and so on. So therefore, these natural constants do actually change. So this is the physical interpretation of this mathematical way, which is, by the way, called renormalization, which is a really important instrument and tool in quantum field theory. And this scaling of these constants is also called the renormalization group. That's what is called. So, however, considering all this, it could still be that we could at some degree get to a distance where, like at a Fern, this breaks down and a different structure occurs. For example, string theory assumes that at some degree there will be strings. There won't be these particles anymore, but there will be one-dimensional strings. So this would be a completely other structure that occurs there. However, it could, of course, also it could also be that this pattern continues ad infinitum. So actually we do not know. But to see this, to get closer to what's actually at a particle level occurring, we need to look closer to see whether this structure at some degree changes. We need to look closer and closer and closer. And looking closer means smaller distances. And in particle physics, smaller distances means higher energies. And therefore, this is the goal of particle colliders, to resolve this. And therefore, they are most of the time trying to build ever larger colliders with ever larger energies. We had an episode about this before, if you can remember, where we also looked at some critique of this. But this is basically the reasoning behind it, that the more energy we put into these particles, the closer we will see those particles, and then we can basically hopefully at some point distinguish whether this pattern just goes on and on and on, or whether a different structure will emerge. So I think in this effect of these fractal structures that are also occurring in nature can also be interpreted in the spiritual, because in Ezekiel 10 it speaks about wheels that are within wheels. So there you also have this, basically the structure where wheels are in wheels, and I guess in those wheels there again will be wheels. So there's also this fractal structure which keeps continuing, and this just shows the eternal depth of God, the infinite depth of God. And what you can also see there is that if you look at the example from quantum field theory of particle physics, where we had these changes, we had changes in the natural constants due to this covering of the charges and so on, and so the deeper we went, it was similar, it was basically the same, but it was also something was changing, something was different. And I think it's the same way. The more we get to know God, the deeper we get, and things in some degree remain similar because it's God, he's eternally deep, but it's also in some sense different because we get to know him better. We get a deeper knowledge of him, we get a deeper revelation of him, and I think that's what he wants us to do. That's why he reveals this in nature, that just as we in particle physics have this urge to look deeper and deeper and deeper into these particles and see what's beyond that, what's even beyond that, and how the constants change there, just like that, God wants us to get to come closer and closer and closer to him, to get to know him better. And as the Bible also tells, that the Spirit it goes into the deepest depths of God, that he wants to take us with him there, that we get a revelation of God that is a close revelation of God, and that we can carry that into this world, and that we can just see him as he really is, and get this intimacy with him that he wants us to have, and that was, if you just look at the biblical narrative, was his basic or his foundational intention with us, that he wanted people he can relate with, that he wanted people he can have intimacy with. So this is basically his longing for us, and this is also therefore our purpose. And I think this is also revealed in nature, that he calls us deeper to him. Episode 36, Neutrino Oscillations. So I'm not sure if I mentioned it on the English podcast, but I think I did. So one of the parts of new physics, or where we do not understand the current physics, are so-called neutrino oscillations. And I want to explain them, or what's behind this I want to explain today, or in this episode. And for this to understand this, we need to first understand what neutrinos actually are. So why do we need them? How do they come about? What are their properties? And they follow from the weak interactions. And just to explain the weak interactions, they are basically responsible for the radioactive decay, especially beta decay. So if we just look at beta decay, what happens in beta decay is that there is a neutron which will decay into a proton and an electron. At least that's what we see. at first. And but if we just do the maths, we just say, okay, one particle decays into two particles, and we just use the energy, calculate the energy, use energy conservation, and see how this fits together, then we will see that the spectrum, the energy spectrum, has to be discrete. This means there are only firm values of energy that can be taken by such a decay. But if we do the measurement and see what happens then we will see a continuous spectrum. We will see that basically all energy values can be taken. So this is a contradiction. So how can this be? So you could say, okay, maybe the conservation of energy is wrong, but this is a well-established law in physics, so we won't throw this out easily. So first, then you say, okay, maybe there's a different particle in there, because you realize if we have a third particle, this spectrum does not necessarily need to be, or it does not need to be discrete. It can be a continuous spectrum. So you just define a new particle. You call it, since you have a neutron, you call it a neutrino, which is basically, ino is basically the Italian way of making something sound more cute. So you call it a neutrino. So it's actually Enrico Fermi, who was an Italian physicist who came up with this concept. And therefore, you have this new particle, which you say will also result from such a decay, and therefore they are needed. So this is really how they come about. They are not basically found in some detector, but basically they are needed to save energy conservation, and therefore we assume them to exist. And of course they have been experimentally confirmed. So in experiments it could be shown that these particles seem to actually exist. But the weak interactions, they have a different, another property that makes them special from the other interactions, like the electromagnetic interaction or the gravitational interaction and so on. And what makes them special is that they behave differently towards particles, not only, but particles of the of the same kind. So what is meant by that? So particles have this property called the helicity, which is basically has to do with their spin and the direction in which their momentum is moving, and they can be in line or they can be not in line, and depending on this you would call them left-handed or right-handed, and this is this left-handed, right-handed is basically the helicity that you can have there. And usually all the interactions do not distinguish between this helicity property. They treat every particle the same, whether it is left-handed or whether it is right-handed. They don't care. However, the weak interaction does distinguish there. So it makes a difference there. And actually it treats them differently. And what it does, it works only, or it acts only on left-handed particles. So it does not act on right-handed particles, but it does act on right-handed antiparticles. But on the other hand, it does not act on left-handed antiparticles. So this is how this works. And this changes things up a little, because as we said, these neutrinos, they are basically just participating in the weak interactions. They are only part of the weak interactions. They are not electrically charged. They do not participate in the electromagnetic interactions. They have no color charge. They do not participate in the strong interactions. And from this part of the theory, they do not have a mass, and therefore do not participate in the gravitational interaction. So this is right now, we will see this will change later, but for now they are considered to be massless. So what this means is that since the weak interaction does only act on left-handed particles, we can the right-handed neutrinos have no force acting on them. All the other forces are not acting on neutrinos anyway, and the weak interaction is not acting on right-handed neutrinos, or on right-handed particles at all, and therefore also not on right-handed neutrinos. So there's no interaction at all acting on them. So they are basically, if you would have a right-handed neutrino, it would go through everything. Would nothing be affecting it. It would just go through space like nothing, and actually would behave like nothing, and therefore we can consider it basically nothing, because we it is nothing. I mean, it does not interact with anything. And this is actually what one does. It says, or one says, it does not interact with anything, therefore they do not exist. So therefore one says there are no right-handed neutrinos. So we just throw them out. This is all fine. So this is basically what the standard model says about neutrinos. However, there are observations which yield problems there. Since, first of all, the neutrinos are particles who are related, of course, to the leptons, which are electron-like particles. And there's not only the electron, but there's also the muon and the taus, which are basically, you can just consider them to be really heavy electrons. They don't change. They have the same charge. They have otherwise the same properties. They just have a lot more mass, and therefore they also decay, which electrons don't. And those also each have their own neutrino. So there's the electron neutrino, there's the muon neutrino, and there's the tau neutrino. So they have their own kind of neutrino, and according to a theory, they should remain their kind of neutrino. So there should be no mixing between an electron neutrino becoming a muon neutrino, or a tau neutrino becoming a muon neutrino, and so on, or mixing all the way between. This should not happen. This is not expected in the theory, and this is not to be seen. However, measurements have shown that this is actually occurring. This is meant what is said by when one says neutrino oscillations. This is meant by this, that those neutrinos tend to mix between themselves, that after some time an electron neutrino might become a muon neutrino and then become a tau neutrino, and so on, that this mixing really does occur in nature. And this leads to problems, because what this must mean, so if you just put this into the equations, if you consider for this fact, then this must mean that the neutrinos do have mass. They need to have mass for this to work. And as I said before, we have considered them massless. Now this is not the case anymore. Now they do have mass. Why is this a problem? Well, we saw in the episode to the Higgs mechanism that the Higgs particle is responsible for giving particles their mass. So actually this Higgs particle is bounding or is interacting with these other particles, and particles that interact with the Higgs particle are basically slowed down, get some inertia, and this is considered to be mass. So since the neutrinos do have mass, as we have found out now, they need to interact with the Higgs particle. So this is a problem, because the Higgs particle does not work like the weak interaction in the way that it says I only work on left-handed and right-handed particles. The Higgs particle is different in that sense, that it says I only work with particles who are left and right-handed. So you need both parts. So the Higgs particle cannot give mass to a particle that is only left-handed, or where only left-handed particles exist, like for the neutrinos. So this cannot work together. So the Higgs mechanism cannot give neutrinos, as they are considered to be in the theory, their mass. So there need to be something different. We need a different explanation for this. And there are different ways to resolve this, or try to resolve this. And the most apparent way is just to say, okay, before we threw the right-handed neutrinos out because they were not interacting with anything anyway, but now let's just get them back, and then everything will work out. And we will even get more of this, because then we can say, okay, these right-handed neutrinos, it will follow from the case that we haven't observed them yet, that they have to be really heavy. And if they are really, really heavy, then they might be something like dark matter. So in a different episode, I'm not sure, I think on an English podcast I sometimes mentioned it, but there is this matter in the universe, dark matter, which makes up a huge part of matter, more matter than we are made of. And this is confirmed now to exist in the universe, and we really don't know what kind of matter this is. We only know that it is not interacting electromagnetically, and also not with the strong force, but maybe it's interacting with the weak force, and of course with the gravitational force, because it's heavy, and that's how we observe it. And therefore, you might say, okay, we have these basically new particles that we restored because we threw them out earlier, and they can be very heavy, so they could be dark matter because they also only interact weakly or gravitationally since they have mass now, and therefore this could be an explanation of this. So two birds with one stone, you might think, but I think this is a little more complicated. There are issues arising then still. That's why this is not really considered. It is still there's still consideration going into it, but not that much. And also, there are other explanations that you could have. You could also, of course, say, okay, we have only left-handed neutrinos, but this is the case because left-handed and right-handed neutrinos are basically the same thing. And this is possible if you consider neutrinos to be Majorana neutrinos or Majorana fermion. This is named after an Italian physicist who basically came up with fermions, which are the particles matter is made of, that are their own antiparticles. So in Majorana fermions are their own antiparticles. So if you have, for example, electrons, this is not possible. They have a charge. The antiparticle has to have opposite charge. So these Majorana particles have to be chargeless, which the neutrinos are, so this works out. And then you can say, okay, they are their own antiparticle, and then left-handed and right-handed neutrinos is basically the same thing, and then you will not have this problem that the Higgs particle cannot couple with them, but you will have different problems that the lepton number will not be conserved, and also there will be different decays occurring, and one of these decays is the neutrino-less beta decay, double beta decay, which is basically a beta decay where there are no neutrinos occurring. And this there are experiments that are trying to observe it, but until now they have not have any luck of observing this decay. But if this would be the case, if neutrinos would be Majorana neutrinos, this decay would have to be there. And then there's a different explanation which says that the interaction between neutrinos does not happen with one Higgs particle, but with a couple of Higgs particles, or two Higgs particles who are coupled and coupled then to the neutrinos. This would lead to the standard model to breaking down, and therefore you would need new particles to account for this. So this would be also not an easy solution. You would have put a lot of work in there. But as you can see, most likely there has to be new physics involved to understand this issue, to explain how these neutrino oscillation can exist, how this can be, how we can describe this in our theories. And I think this can also be interpreted spiritually, especially this part of right-handed neutrinos who basically interact with nothing, who go through everything, who do not interact with anything. I think this can be considered as an image on as us Christians who are in this world, but as the Bible tells us, who are not of this world. So we are not influenced by this world. We are not part of this worldly cycle, but we are part of a different world, the heavenly world, where we are placed according to the Bible and in our spirit, of course. And while we are in this world, we are not of this world. And this can be seen there. So we, as these neutrinos do not interact with anything in this world, with any of the forces that try to push them around, as they just are oblivious to them, we can basically be oblivious to any forces in this world who are trying to push us around, because we are not of this world. And just as if you consider it further with the neutrino oscillations, that neutrinos have to have mass, and therefore these right-handed neutrinos are not just so non-interacting that they basically do not exist, but maybe do exist and are gravitational, do participate in the gravitational interaction. This would also mean that, especially if they are really heavy, then they have, not only are they not influenced by other things, they influence they influence the world, basically. So, and this, I think, is an image on the Christians, as Jesus said, that we are the salt of the earth, that we are the light of the world, that basically this is something we are, that we attract people to this other world that we are a part of, and that we are, by doing this, we are, however, not influenced of this world. Another thing which this neutrinos show, which I also mentioned in my blog post, which you can read on sci-faith.substack.com, is about that this also shows that science can be in some degree considered to be a faith. Because, as I mentioned in the beginning, we had this law of the conservation of energy, which seemed to be not fulfilled according to this continuous spectrum instead of a discrete spectrum, which would result from from a decay of one particle into two particles. And instead of doubting that, instead of throwing the conservation of energy out, we just assumed there to be a new particle. So we had that much faith in this law of the conservation of energy, that instead of when the results were not showing this, throwing it out, we just fix the theory to account for that, without even knowing that these particles actually exist in the beginning. And I think this shows that there is some degree of faith already present in scientific theories, and I show this deeper in my blog post, so feel free to look into them. There I show how this can be related to science also being some kind of faith. So that's everything for today's episode. I hope you liked it and you enjoyed each part of it. If you want to get in touch with me or discuss a topic or want to give me some feedback, then feel free to contact me using the contact form on my website, sci-faith.de/en. And there you can go to the contact tab and contact me. And if you have any other things or episodes you want to have covered there, or topics you want to have covered, feel free to contact me there. Also, if you are not yet familiar with the format in which this podcast is produced, let me just briefly explain it to you. So there is always at the beginning of a month or of a block, there is a big block of 4 episodes in one thing. It's kind of like a preview, which I call it, where you have the next 4 episodes all in one episode together, combined. And this is for people who like to hear long format podcasts, who have a long way to work or something else, where they can listen to a long episode and can then have a preview of the next 4 episodes all at once, and are completely up to date from the beginning of the block. For those who like their episodes shorter, who prefer it if they have a half an hour or even less of a podcast episode, for those there is every week afterwards will appear a podcast episode almost in that length, and this way I can publish every week a new podcast every episode, and everyone can have it his own way, either once a month a long chunk of content, or once a week a shorter format podcast episode. So I think that's the best way for everyone, and also for me when I'm producing it. Please also note that this is an independent podcast, which means that it is recorded, produced, and marketed by me. So I really need your support in this. So if you like this podcast, then give it a 5-star rating. And if you have the time, even write a review to it. This just helps other listeners to become aware of this podcast, and then people who might be interested in this content can become aware of it. Also, if you have friends who you think would like this content, then recommend it to them and share it with them. Also, you can support me in other ways, for example by reading my blog and subscribing to my newsletter, or even by reading my books, which you can find on Amazon. For example, there is my latest novel out now is Alien Thoughts, which is pretty entertaining from the feedback that I gotten, and so it's also in some way related to science and faith. The topic of it is also in there, but of course you can also read the book to this podcast, Sci-Faith, The Compatibility of Science and Faith, which is also available in English since last year. Thank you for that. And now I wish you a wonderful day, and I'm looking forward for you to tune in again next time.